Okay, since you're kind of going quiet, we might as well start. Right, so I'm just going to remind you of where we were last time, because the last few slides we went through quite quickly, just in the last 5 minutes. So I'm just going to remind you of that and set the context before we go on to calculating the intensity distribution of a finite-sized single slit. So, right. So I ended the lecture by basically introducing the idea of Fraunhofer diffraction. I mentioned the sort of the full theory of Fresnel diffraction, where you kind of make no approximations in red, so off syllabus, but that's the theory that works for every case, basically. You know, you don't do any of this sort of long distance, small angle approximation. We have been working in, and we are going to continue to work in the Fraunhofer regime, which is a simplified treatment when essentially, as we discussed, it applies when the phase of the light amplitude varies linearly across the size of your diffracting object, your diffracting aperture. Okay, now I also mentioned the fact that in the general case, we've got some sort of arbitrary, the light's not quite, hang on, let me go up. That's better, isn't it? That's the normal level, isn't it? Right. Right. So I mentioned that in the general case we have some sort of arbitrary aperture in principle, and what we're going to want to do is assign a complex amplitude to every infinitesimal point source in that sort of continuous object, and then sum them up to get our final amplitude. And obviously for continuous objects like this, as opposed to just the two narrow slits, that sum is going to become an integral. So that's where we're headed. And I also mentioned that when you do this, when you construct these integrals, it turns out to be what's called a Fourier transform. Some of you may know about these things, or at least have heard of them. Some of you may not, but you cover that in detail next year. I then sort of mentioned that the Fraunhofer regime applies when you're or the easiest way to get into the Fraunhofer regime is when your source, your light source, and your image are at large distances from the diffracting aperture. And in particular, you need distances greater than this a squared over lambda. A is roughly the size of your diffracting aperture. And I sort of did a sort of optional proof to sort of hopefully convince you where that comes from. Otherwise, it looks like it's just plucked from nowhere. I then mentioned that actually the key thing about this, if you're a long way away, is that it means that you've got plane waves impinging upon your aperture, and if you've got plane waves, then you are in the Fraunhofer regime. And then I mentioned that actually you can also more practically use lenses to create and observe your parallel beams rather than having to be at very large distances. Okay, so I said that. Then, okay, I mentioned that plane waves definitely are a sufficient but not necessary condition, and we'll come across some other cases later, possibly later in this lecture or at the very beginning of the next, to see how you can be in the Fraunhofer regime even without plane waves. Right, so, okay, that was a recap. And now the first interesting problem that we're going to look at today is that of single slit diffraction. And by single slit, I mean a single finite width slit, which I'm going to say has a width b. Okay, so what we're going to do is shine light onto a single slit and just try and work out what the intensity distribution looks like. So up to now, when we've shone light on slits, they have been what's called ideal or infinitely narrow slits, right? Those two things, if you see them written down, mean the same thing. If you are told you've got an ideal two-slit experiment, it means your slits are infinitely narrow. So that's what we've been dealing with so far, and we've been treating those cases such that those infinitely narrow slits form a new point source, basically, so your waves are spreading out cylindrically or circularly, if you take the 2D slice, from this source. Now, the difference here is that now we've got some finite-sized slit. So we've got we've got an infinite number of infinitesimal sources all the way along this slit, each producing its own circular wave pattern. So what we're going to need to do is add up the complex amplitudes and see what we get for the intensity. So just before doing that, I'll just give you, my laser's working, a little demonstration of what a single slit pattern actually looks like. Which one shall I choose? Let's do the middle one maybe. Okay, so, okay, so I'll try and do it on the ceiling again. Try and get my nose out of the way. Right, can you see it there? Oh, hang on. Can you see it there? Oh, my laser's a little bit temperamental today. Right, so that's what single slit diffraction pattern looks like. And so you can see it was sort of brighter in the middle, and then you still had some sort of peaks in intensity, but fainter. So we're now going to figure out the full form of that intensity distribution. So here's our picture. So my slit is of width b, as I've already said, and I'm using a coordinate system so that my origin is going to be in the middle of the slit, and so this sort of thinner blue line is a ray representing a ray coming from the source that's in the middle of the slit, and it's going off to a point that we want to observe the pattern at. And then I've chosen another point source at a distance x away from the middle, and the ray coming from it is represented by this thick blue line. And we are working in the Fraunhofer regime, we're working at large distances so that these rays are parallel in the usual way. So this looks very much like then just the two-slit diagram, right, where our 2 point sources are separated by this variable x now rather than the constant d. But that means that the mass is completely the same for what we've got to do. So what we've got is a path difference given by x sine theta, path difference between the rays coming from these 2 point sources, or a phase difference of k delta, which equals k x sine theta, right? So hopefully that looks very familiar to you, but just the old d for the two slits replaced by this variable x. Okay, so what we want to do now is basically assign a complex amplitude to every single one of the point sources and then add them all up, which is going to be an integral. So here we are. So we're going to have something that looks like this. We're going to assign an e to the I k delta to every one of our infinitesimal point sources, and we're going to sum them up, and we're going to have to add them across the whole width of the slit. So the limits of this integral run from minus b over 2 to b over 2, given my coordinate system of having x equals 0 in the middle. So let's actually do that properly. So that was just sort of a summary of telling you where we're going, but now we're about to do this calculation properly. And I'm actually not going to work in normalized units for this calculation, just so that you can see all the constants as well. So, okay, so what I'm saying is that the complex amplitude from a point source at position x and infinitesimal width dx is, okay, so I'm going to write it as this. This term I will explain in just a second. E to the I k x sine theta. Right. So what I'm saying here is that A0 is going to be my amplitude from the full slit. So what I'm writing here, so this part, this coefficient, is the real amplitude of my little infinitesimal point source, right? So I've got the full amplitude that comes from the full wave divided by b to make it an amplitude per unit length, multiplied by the width of my actual infinitesimal source, right? So this is the little bit of the amplitude assigned to that particular point source. And then multiplied it by the exponential term, which encodes our usual phase difference. Okay, is that clear to everybody? Sometimes that A naught over B confuses people, but anyway, okay, hopefully it's clear. Let me know if not. Okay, so to get the total amplitude, we're just going to add them all up, i.e. perform an integral. So A is going to equal A naught over B integrate over the full width of my slit, e to the I. Okay, have I done something wrong? Sorry, have I done something? Oh no, sorry, I heard some mutter, thought I'd made a mistake. Okay, right. So that's the integral we want to do. A naught over B. Right, so I've got 1 over I k sine theta e to the I k, x sine theta from minus b over 2 to b over 2. Right, let's do that. That's a naught over b. Actually, let me over I k b sine theta e to the I b over 2 k sine theta minus e to the minus all that stuff k sine theta. Sorry, it's a bit squashed there. Right, hopefully you recognise that bit in brackets. That is just a 2i sine half kb sine theta over I kb sine theta. So the i's are going to cancel. And I'm just going to rewrite this in another form. Well, I'm just going to bring the 2 down to the bottom, basically. So I've got a naught sine half kb sine theta over half kb sine theta. So that is your expression for the total amplitude coming from a single slit of width b. Okay, so next slide just summarises that. There's the answer. Here on the slide I have suddenly now worked in normalised units, so you've got nothing out the front because, as we've said many times, once you sort of square it and write the expression for the intensity, you just bung a constant at the front, which is, gives you the correct normalisation. The reason I wanted to keep the A0 here in the derivation is because I just wanted to explain this. Otherwise it looks like just dividing by a 1 over b is a bit random, but hopefully if I keep the full A naught in there representing the full amplitude, you understand why that 1 over b is in there. It's just a sort of this whole thing together is a little bit of real amplitude assigned to that point source. Right, so let's, as the slide says, just to save us a little bit of writing, let's call this half kb sine theta beta. So I've got A equals A naught sine beta over beta. I expect many of you will recognise this function. You've probably had to plot it in your time. Sine x over x, and it has a name. It's called the sinc function, so sinc beta. Okay. And the intensity, of course, goes as the square of that. So now I'm just going to convert that into this I naught is A naught squared, sine squared beta. And that is our final expression for the intensity. Everybody happy with that? Okay, so what does that thing look like? So this is the sinc squared, this is the intensity distribution. So you see this big central peak, so at beta equals 0, here you've got sine of 0 over 0, which is 1. Right? And then as you go away from 0, both beta and sine beta increase, but beta is of course increasing faster, so you see this drop in intensity. Some point it gets to 0, and we'll consider this point here where it drops to 0 for the first time quite a lot in a minute. It's then going to rise again, you get these subsidiary maxima roughly, but not quite, at 3 pi by 2, 5 pi by 2, etc. Okay. So, right, so let's look at where the first zero happens. So that's going to happen, first zero in intensity. So that happens when sine beta, well, when sine beta goes to 0 for the next time, not another centre. So let's say beta, which equals half kb sine theta equals plus or minus pi. That's when it'll go to 0 either side of that central peak. And we can solve this to get it in terms of wavelength instead. So here we've got sine theta equals plus or minus 2 pi over kb, which is plus or minus lambda over b. Right, so what we've got here is an expression for, in terms of lambda and in terms of the slit width, when our intensity distribution drops to 0 for the first time. And this width, what we've got here is basically a measure of the width of this central peak. And that's going to be important for where we're going. And what you can see as well is that what you've got is significant diffraction effects if your slit width is very small, particularly if it's comparable to the wavelength of the light that you're working with, or if you've got a very, very large slit, very, very large aperture, then your diffraction effects are very small, right? And this is, we'll talk about it probably tomorrow, but this is why, telescopes, for example, you want very, very large diameter lenses because you want to reduce the effects of diffraction. Okay, so what we calculated here, I'm just also generally, because we are working in the small angle approximation, I'm also going to say, right, so theta strictly equals sine to the minus 1, lambda over b, but that just is approximately lambda over b, right? Theta equals lambda over b. Okay, so this definition that we've done here is strictly called the half width at first 0. That's the distance we calculated, the distance between the central peak and the first minimum. It's giving us a measure of the width of this peak. More usually, you might characterize the width of a peak with the full width at half maximum. So if I just draw on a sinc squared function. Right, so here's roughly a sinc squared function. We've calculated that distance. More usually, let's call that I over I0 or something. More usually, that's supposed to be a half. I don't think it's quite a half, but you would calculate the full width at half maximum to characterize a peak. Certainly, you will come across that in various contexts if you haven't already. The reason we're calculating something slightly different, what we're trying to do here is characterize the width of the peak, but it turns out that this distance we've calculated is very much easier to calculate than the full width of at half maximum, and it turns out to be roughly the same number. It still goes, the full width at half maximum still goes as lambda over b. It's just got some proportionality constant. I'll call it c, which is roughly 1 still. So they're about the same size. So that's why we do it this way. Okay. Now, what's the point of all this? Why am I sort of stuck on talking about trying to characterize the width of this peak? This becomes important when what you're trying to do is resolve two objects, right? Now, we're not yet talking about lenses as such. We're going to get there. We're talking about slits. But just imagine, well, I'll give you a sort of heads up. This same sort of pattern is going to occur when we're using telescopes as well. So just imagine that what you're trying to do is, you're looking at some distant stars or something like that, and you've got two of them, and you want to know, am I seeing two objects or am I just seeing one, right? There's going to be some sort of resolution that goes on. If these stars are very, very close together, it's going to be difficult because each of these objects is going to emit light and they're going to produce some sort of diffraction pattern. One object will look like that, the other object will look like this. And you can imagine that if these peaks become too close together, you can no longer tell if you've got two distinct objects or just one. So we need some sort of criteria to tell us or to define what do we mean by distinct, what do we mean by being able to resolve that these things are two objects. And traditionally, the so-called Rayleigh criterion is used, and this says, and I'll write it in a minute for you to fill in this box, but I'll say it in words first. This says that two objects are just resolvable if the peak of the diffraction pattern of one coincides with the first minimum of the other. And of course, they're easily resolvable if it's further away than that, right? So if these two peaks were further separated, we'd be fine. But if they're closer together, then things get difficult. Okay, so let me just write down something, sort of a formal definition for you to put in that box. So this is the Rayleigh criterion. So it says two diffraction limited images are well resolved if well resolved when the maximum of one diffraction pattern coincides with the first min of the other. So first minimum of the other. So this means that you've got an angular resolution which equals sine to the minus 1 lambda over b, where b is the width of your slit. Also, perhaps note in the box that alternative criteria are available. Sometimes use alternative criteria can also be used, right? This isn't the only one, but it is the most common one. It's also, in this day and age, not true to say that this really is the absolute limit for when you can... it's a rule of thumb, right? It's not the absolute limit for the best you can do. These days, in fact, you can do really quite a lot better than the Rayleigh criterion if you know what you're doing. There's a whole field of physics called sub-diffraction imaging, so it's quite a hot topic. But certainly this remains true, that this is what you can do with relative ease. Okay. So now we've got to here, and we've got sort of all the things I wanted to talk about, all the tools in the bag, as it were. I want to go back and look at the resolving power of the diffraction grating. So we're just going to go back to the diffraction grating for a little while. We saw in another lecture, either lecture 2 or 3, I think it was 3, a sort of hand-wavy basic way of calculating the resolution of the diffraction grating. But now we're going to think of it more mathematically, more in terms of proper diffraction effects. Right, so resolving power, right, so the question we're trying to ask is, what is the closest separation of two wavelengths that I can tell really are two different wavelengths as opposed to just an error, right, on a single wavelength. So I'm trying to see, so this is characterized in terms of something called the resolving power, which is defined as lambda over delta lambda, right? So delta lambda is the smallest wavelength separation that I can resolve at the wavelength lambda at which I'm working, right? So this is the quantity we're trying to construct and calculate. So we're going to go back to this diagram, which we've seen before, just to remind us of the dispersion of a diffraction grating. So hopefully you remember this. And we calculated this quantity called the dispersion. We started off with our diffraction grating equation. We did some implicit differentiation to get this relationship for d lambda by d theta, which I'm going to write up on the board because I'm going to need it. Okay, so starting from here, we got d lambda by d theta equals d cos theta over n. And I said, right, this is the relationship that we need if we want to know, if we have some sort of difference in angle at which we're seeing our peaks, we can convert that into a difference in wavelength via this conversion factor which I've just calculated. Right. So d cos theta over n delta theta. Okay, we're going to need that for where we're going, and we've already seen that before. Okay, so then let's remind ourselves of the diffraction grating setup as well. So here we've got our light source. We're making it a point source by putting it through the single slit. Here are our light rays. We've got a collimating lens to make our plane waves, our nice parallel rays. The diffraction grating is then then causes the light to bend through some angle theta, right? And then we can view it on the screen as well. Right, so our question is, we want to know, this is the dispersion caused by a diffraction grating. We want to calculate delta theta, our sort of limiting angular resolution, and we know from our arguments on the single slit or sort of single slit aperture that it's going to go something like lambda over b. That's our limiting angular resolution. But the question is, what is the relevant b in this question? It's something that characterizes the size of the aperture that we're working with. Right? We're not dealing with a single slit now, we're dealing with a diffraction grating. Well, it turns out that the thing that's important actually is just the width, essentially, of this parcel of light. That's the thing that actually characterizes, is the correct characteristic width to go in here. So if my diffraction grating has a width w, and it's bent, diffracted through some angle theta, then hopefully you can see that that angle is supposed to be theta. Therefore, if I were to make a perpendicular here, then that, hopefully you can see the geometry because I'm not pointing very well. There's a little angle in theta there as well. So hopefully you can see that the width of that parcel of light is given by w cos theta. Right. So in this case, this is going to be my characteristic width. And then let's put it all together. Right. So we've got some sort of pattern. We know that our first minimum occurs at a delta theta is lambda over this width, which we've now said is going to be w cos theta. That's going to be our limiting angular resolution, and so we want to turn that into a limiting delta lambda. So let's put it all together. Right, so delta lambda equals d cos theta over n lambda over w cos theta. You can see that my cos thetas go away. So I've got d lambda over nw. And so lambda over delta lambda, which is the thing that we want to calculate, is nw over d. W is the width of the diffraction grating, d is the separation between the slits, and so I could just write that, if I want to, as n big N, where that is the order at which we are observing our pattern, and this is the number of slits on the grating. Okay, so what that is telling us is that our resolving power depends only upon essentially the size of the grating, the number of slits that we have. We want a large number of slits for good resolution, and of course also the order that we're actually observing. That, by the way, I'm sorry, that bit from where I put it all together, hang on, from here onwards was the stuff that was supposed to go on that slide down to that derivation, and then you can see the result at the end of that slide. Okay. So the bigger your grating, or the more the number of slits on your grating, the better is your angular resolution, and therefore the better your resolving power. So a big number here is a good thing. It means that a particular lambda, you can resolve very, very small wavelengths, right? So if you're trying to, look at sodium or something with the two wavelengths, right, you want a good grating to be able to actually disperse those wavelengths and be able to recognize that you have two separate things. Okay. So I just want to return to something that I have promised since about the first lecture, I think, which is to talk, now again that we have the tools to understand this a bit more, I want to talk about what's going on with a more realistic two-slit experiment. Right? So everything we've done so far has been, everything we did with the two slits and the diffraction grating, sorry, I qualify, was with this sort of ideal case where we had infinitely narrow slits. However, right, now let me just remind ourselves of what happened for the ideal two-slit case. So we derived this, was given by I0 cos squared half k d sine theta. Hopefully that rings a bell. So this was just a pure cos squared pattern, I over I naught. So it looked like this. What should I plot it as a function? I'll plot it as a function of sine theta, so that I know that that's lambda over d, that was 2 lambda over d, that's where our peaks were. I'll carry it on a little bit this side. Right. Now all these peaks, I don't know how well I've drawn it from your perspective, probably not well, but they're supposed to be all the same height, right? There's nothing in that expression that suggests anything other than that this is just a cos squared, everything's of the same height. And yet, when I showed it to you, which I'm going to do again, when I showed you what it really looks like, we saw something a little bit different. Right, you can see, again, in fact, it feels like it's looking a lot like the single slit. It's not quite, but what you're seeing is that it's much, much brighter in the middle, and then the intensity decreases, right? And I promised you right from the first lecture that I would try and explain a little bit about why that happens. So that was a two-slit. I was shining it through. This is the calculation we've done for a two-slit. Clearly doesn't look quite the same. So what's actually going on is that, of course, we never have the ideal case. We never have infinitely narrow slits. Our two slits, in reality, are always going to have some finite width. And so what we've got, as well as the two-slit interference going on, is that we've got single-slit diffraction going on as well. Now, it turns out, and I'm not going to prove this because it's in the problem sheet, so this is for you to do, but it turns out that in the real case, real two-slit case, the intensity distribution isn't just the simple cos squared. It actually looks like this. It's got the cos squared term. But then it also has a sinc squared term. Did I hear an oh? Was something, has someone already started doing the problem sheet or something and we're wondering what all that was about? I don't know. Okay, so that's what your intensity distribution actually looks like. Now there are very good reasons that it ends up looking like that, which I won't go into because it will become a lot clearer in the second year once you've done Fourier transforms. However, you will do it, I think it's the very last problem in the problem sheet, as a sort of brute force method essentially of calculating this, which you're asked to do. This is the answer that will come out. But what's actually happening here is that you've got your ideal two-slit pattern, so that's the ideal, if I could spell, two-slit interference, and it is being modulated by the single-slit diffraction pattern. I'm going to plot this in a minute to give you an idea of what it looks like. So, the way I always draw it is to basically draw a single slit diffraction pattern first with sort of dashed lines, sort of envelope like this. Right, and then you've got your two-slit interference going on underneath as well. And this is what you actually see, and this is what we were seeing on the ceiling. Right, so what you see is something more like that, hence it's much brighter in the middle. Okay, so let's talk about that a little bit more actually. I mean, it's sort of browny, so it's something you should know about, but not strictly on syllabus, but it's still perhaps interesting, and interesting things to point out. Right, so I'm just going to mark on some interesting points. I'm plotting this, let's say, as a function of sine theta. So that first minimum in the single slit diffraction, as we just calculated, is at lambda over b. Okay, so if you want to make notes on this, sorry, you're going to have to use a separate bit of paper because, as I say, it's off syllabus, so this is just a bonus extra you're getting. So single slit, the first minimum is at, sine theta equals lambda over b, as I've just written on. Right. Now, also remember that the two-slit maxima occur when n lambda equals d sine theta. So d is the separation between my slits, b, as before, is the slit width. Right, so sine theta equals n lambda over d. So we can do a calculation for basically how many bright fringes we think we're going to see roughly in this central region. In that central region there. So roughly when these two things are equal, when the sine thetas here and here are equal, we get the equation, well, I'll put when they're equal we get that. So the number of fringes that we're going to see is roughly given by d over b. Number of fringes in central, what should I say, in central diffraction peak or something. Right. Okay, so you can spot a few things from here. So first of all, clearly you're not going to see any fringes at all if this isn't a very exciting statement I'm about to make, but you're not going to see any fringes at all if d is less than b. Well, that makes sense, right? That would be a slit separation less than the slit width. Clearly, that's not working. If you've got if you've got a very, very narrow slit width, then you will see many, many fringes. And what's actually happening there is that you're reducing essentially to something much more like the ideal case. So if b is much, much less than d, the slit width is much, much less than the slit separation, your single slit diffraction pattern is very, very broad, right? And so you end up with something looking much more like the ideal case. Right, so that justifies something I said earlier, which you may or may not remember, that I said when you're dealing with slits of a finite size, you just have to worry about them being small enough, right? You can get close to an ideal pattern as long as your slit width is much less than the slit separation. It doesn't have to be absolutely infinitesimally narrow. It's the relative sizes that really matter. And then another point of interest is that if, for example, so that was sort of number one point of interest, if d is some integer multiple of your slit width, then every nth order in your pattern is actually missing. So I'm going to put e.g. m equals 3 because what you may not have noticed at the time, but I tried to draw it quite carefully, what I drew up there was exactly for the case where m equals 3. So what you can see then is that you've got your 0th order, your first, your second, and then number 3 is missing because I drew it for exactly this case so that I could point at it now. Right, so that's something called missing orders in a diffraction pattern. So in your problem sheet, where you have to derive that intensity distribution, it might ask you to talk a little bit more about it, or these are the sorts, maybe it doesn't, but these are the sorts of things that you could have thought of to say. Right, so we're now sort of entering the last stage of the course, actually. We're going to now talk about two-dimensional diffraction. So up to now, or diffraction at two-dimensional apertures, I should say. So up to now we've been talking about infinitesimal slits, so very long in one, sorry, not necessarily infinitesimal, but slits that were very narrow in one dimension, and we were envisaging them to be very, very long in the other dimension, right? So we were only worrying about the diffraction in the narrow dimension, and not worrying about the long dimension. But in reality, of course, slits are have 2 dimensions, right? Normally we're talking about rectangles, not about something that is, infinitely long in one direction. So this is not, again, not on syllabus for you to be able to derive, but it's not very difficult to do. It is, again, on syllabus next year instead. But let's just talk about how you would deal with it. So basically, you'd have to, your complex amplitude, you'd have to take care of both dimensions, essentially. So you would end up with a complex amplitude that looks like this, and you're going to have to integrate over both the x and the y dimensions, essentially. And if you do that, I'm not going to do it, it's done in Hecht, it's not very difficult to do, in fact, but the result comes out quite nicely, actually. It turns out that you just get a sync pattern in both dimensions, sort of independently. So what it would look like if you were actually sort of looking top down on what you get is one sort of intensity distribution from one dimension, and then you get another one that looks like this from the other dimension. That's basically what it looks like. Okay, but mostly we are dealing with slits that, even if not infinite in the long dimension, they are still much longer than the actual width. And in that case, normally we don't really have to worry about integrating over both dimensions, because you get significant diffraction in one direction. Remember that the angular width goes as lambda over b. So if you have one dimension that's much longer than the rest, than the other dimension, you're going to get only small diffraction effects there, and it's sort of, incorporated it into your central peak anyway, so it doesn't really, you don't really see it. Right. Okay, let's talk about circular apertures, because this is going to be very important for where we're going in the next lecture. So this is another interesting case, and in fact it is the more usual case, or the most usual case for actual practical pieces of optical equipment. So if you think of telescopes, microscopes, they've all got sort of circular lenses, or various things have circular apertures, so we need to talk about that. Now it turns out that if you, let me just rub a few things off this central board. Right, so just as I said you want to integrate over both the x and y dimensions for that rectangular slit, if you've got a circle, of course, you would also want to integrate over the whole thing. The best coordinate system to use for that would be plane polars, as it turns out. Again, it's done in standard textbooks like Hecht, but this bit is in brown, so I direct you to that to see it if you want to. This is a bit more complicated to do. The rectangular one is quite easy, actually, but the circular one is a bit more complicated, and what you get looks like this. Okay, so the intensity distribution looks like this, where R is the radius of the aperture, and what J is, J1 is called a Bessel function, right? And you probably won't have come across them yet, hence I don't expect you to go away and do this integration to get that answer. But basically a Bessel function is a solution of a particular kind of differential equation, which you will come across again in the second year. Keep directing you to the second year. But you'll come across it a lot. It comes up in various different contexts, the Bessel differential equation. Okay, right. So what do you actually see? Well, it turns out that the diffraction pattern from this actually, if I take a cross-section of it in one dimension, it looks very much like the single-slit diffraction pattern. So what that looks like as a slice through it is something like that. It looks a lot, sorry, my axis is not very horizontal. Okay, looks a lot like that. Key difference is that first minimum happens not at just lambda over b, the width of the slit, but it happens at 1.22 lambda over w. Should I call it w, or should I call it d? Yeah, w is the diameter, basically, of your of your aperture, of your circular aperture. So you'll recognise the lambda over W bit looking a bit like lambda over B, but the 1.22 factor just comes from the form of the Bessel functions, basically, if you need to solve that thing that I've just drawn there and figure out when it first goes to 0, and it just turns out that the 1.22 comes from that. Now, I would mention, actually, that when you do questions, like exam questions or anything, or problem sheet questions, when you are talking about circular apertures, and you might be asked questions about, when does the first 0 happen, what is the limiting angular resolution or something, you will get a point for remembering that 1.22 factor, right? Of course, it's, it basically goes as lambda over W, but the examiner will probably be looking out for, do you realise there's a 1.22 factor when you're talking about circular apertures? So try and remember that. Okay, so what does this look like? This is a more proper picture of what it looks like. So here's the diagram I was trying to draw, but in 3D, and here is a real photograph of green laser light impinging on a circular aperture, and you get this very bright, this is called an airy disk, basically. I'll even write that because it's worth you knowing the wording. Imagining looking top down on this thing that I've drawn. So you get a very bright airy disk, and then you get other sort of fainter circles, but extending out really quite far. The vast majority of the intensity is in the middle, but still you've got these faint rings, and this is actually a genuine problem in reality. This is the sort of pattern you get when you are trying to look at a star with a telescope. And so let's imagine you're wanting to search for an exoplanet or something, right? You've got a planet, it's close by a very bright star, let's say. The star itself is producing this airy disk sort of diffraction pattern, and the planet is going to be somewhere, hidden in these rings, and generally much, much fainter than the star. So it's quite a difficult thing to do, and yet it's, very a problematic thing, because we cannot get rid of, diffraction effects are always there, basically. I say we cannot get rid of them. As I said, there is this field of subdiffraction imaging, which is a very clever thing. But anyway, it's a fundamental limitation, this diffraction. Okay, so this is going on to, I'm going to stop quite soon, I think, but I'll at least do, let's say, 1 or 2 more slides. So this is all leading to thinking about the resolution of a lens. So if we think back to last term, we were really talking about perfect lenses. We were imagining perfect lenses in the sense of that they didn't have any diffraction effects. We did talk about aberration, so we talked about spherical aberration, chromatic aberration, things like that. We talked briefly about that at the end of the course. But we kind of know how to deal with those things, right? We can do, I don't know if you remember the more complex sets of sort of eyepiece lenses that I showed you in telescopes and things, all designed to try and get rid of those other aberrations. But we're always going to have diffraction unless we can have infinite-sized lenses. So in the geometric optics course, we were basically assuming that our lens was very, very large, that if you could get rid of all aberrations, you could form a perfect point-like image. But in reality, we can't do that, and we know that now, because this is what is defining the size of our image. That is the best we can do. So really, you want very large telescopes and things like this, so large apertures. Okay, what else am I saying there? Right. Now, it may occur to you to think, well, why are you talking about lenses? Because what we've actually dealt with here is apertures, right? A hole or some sort of, circular-shaped aperture, not actually a lens. Now, I'm sort of telling you here that lenses behave in the same way as an aperture, and maybe to understand that, that's what I'm saying in this second bullet point here, what you can think about, the best way to think of a finite-sized lens is to think first of it as an infinite perfect lens, right? Now, if you could have an infinite perfect lens suffering from no other aberrations and infinite in extent, you would have no problem at all, right? You wouldn't have diffraction effects either, because this thing would go to 0 if W is infinite. So you can think of it like that. That's going to produce a perfect spot, perfect point-like image of a point-like object. And then you can think of what the behaviour of a finite size does, is that you can just imagine that this perfect lens has been preceded by an aperture of width W, right? So you can model it like that. And maybe if you do that, you can understand why a lens is also going to behave the same way as a hole of the same size. Right. So we know then, because we've just talked about the Airy disk, that our angular resolution of our lens is going to be given by this 1.22 lambda over W. And this is really a fundamental, it's probably the most important result in practical optics, that whatever you do, however much time you spend on perfecting your lens to get rid of all sorts of other aberrations, you're going to be fundamentally limited by diffraction. So I think I'm going to stop there because it's a nice, easy point to stop, and we will continue tomorrow talking about telescopes and microscopes and more practical pieces of equipment. Thank you.